In this video, we're going to look at galvanic cells. I think you're going to like this. And it's basically a device that'll change chemical energy to electrical energy. We're going to run these redox reactions in two separate containers, and we're going to force the tiny little electrons to flow through a wire in order to go from the oxidation side to the reduction side. Poor electrons. It says the two half reactions are placed in separate compartments or beakers or something like that. And the electrons will pass through a wire as they are consumed in the reduction half reaction. This is going to be so fun. Here's a very typical galvanic cell. I'll set this one up in class for you. Hopefully it'll work. This is probably scaled down to net ionic again. The one that I'll use in class will be a solution of copper nitrate and then solid zinc. And then I would have had zinc nitrate in solution and solid copper on the product side. So the way they've got this listed is fine. The nitrate and nitrate are spectators. This is aqueous. This will be a solid. We'll form a solution of zinc nitrate and solid copper, but the nitrate ion stays aqueous on both sides, so we can can him. Get rid of them as a spectator. And then again, okay, here's a good review of net ionics. Often people kind of do that. They cross off the spectators, but they don't write in the charges. When you write your final net ionic equation, you can't just leave this as Cu. Cu is like solid copper. No, we mean for this to be copper ions from the solution. So you have to make sure that you go through and put charges in for anything that you mean to be an ion in solution. You can cancel off the spectators, but don't leave that as like just Cu. They'll assume that you mean solid copper unless you put that charge in. Oh yeah, copper ions swimming around in solution. All right, perfect. So we can separate the two half reactions. And again, often it's easy to see what goes together. I mean, this copper ion will probably go with the solid copper, and the zinc probably goes with the other zinc. And so you separate the two halves, and then we balance them. So for example, one of the halves was the solid zinc, forming zinc plus 2 ions. There's one particle of zinc on both sides, but to balance the electron transfer, we need 2 electrons. Kind of the opposite with the copper half. I have copper plus 2 ions that'll need to gain the 2 electrons to form the solid copper. Well, this is just perfect. Oil rig. O-I-L-R-I-G. Oxidation involves losing, so we'd say the zinc is the oxidation half. Or you can kind of look at like the charge on the zinc. If you're losing electrons, the charge becomes more positive because I'm not changing the number of protons. So, oh yeah, it started out at zinc. The oxidation number of solid zinc would be 0, and then it turns into a plus 2 ion. The rig part of this, the reduction half, is the copper. The charge on the copper is being reduced from plus 2 to 0. Reduction involves gaining electrons. If you gain electrons, you should become more positive. I should say more negative or less positive. Cool. So the electrons are flowing from the zinc half to the copper half. And we had said there has to be a give and take of electrons. There will always be reduction and oxidation together. Okay, so when we do this redox in an electrochemistry situation in a galvanic cell, we're going to call one of these the anode and the other is the cathode. Here's how I remember it. An ox and a red cat. And then you finish the rest of the story. An ox and a red cat walk into a bar.
An ox and a red cat are trapped in an elevator. I don't know. You can do whatever you want. But that's actually how I remember it. At the anode, you will have oxidation. Reduction occurs at the cathode. An ox and a red cat. Or whatever else you want to think of that helps you remember. Electrons flow from the anode to the cathode. I guess it kind of goes in alphabetical order too, like from the anode to the cathode. But I always remember like the electrons are lost in oxidation, gained by reduction. So the anode is the oxidation, the cathode has the reduction. An ox and a red cat. Okay, are you ready to see a galvanic cell? I mean, this is going to hopefully live up to all your hopes and dreams. Wow, it's beautiful. I will set one of these up in class. Hopefully it works. Okay, so we're going to have two beakers. We're going to separate the two half reactions. I mean, these are very simple. And everything that we label on here is what you're expected to know in terms of these galvanic cells. This is very common to find on the AP test. They might have a picture of a galvanic cell, and they'll have you like interpret what's happening. They'll have you label all of these parts. This is good stuff. Okay, so we're starting with an ox. The anode has the oxidation half reaction. The oxidation half reaction looked like this. It was the zinc solid forming the zinc plus 2 and 2 electrons. This was the zinc aqueous, the ion. All right, so here's how you set up your anode. You take a solution. I'll use zinc nitrate. It could be any aqueous zinc solution, zinc chloride, something like that. It's usually 1 molar. We'll put that in, 1 molar. Like when we do calculations to figure out like how much current is flowing through the system, they'll list under standard conditions. One of those conditions is that your solutions are 1 molar. Okay, so there's the zinc ion part of this. The nitrate is really just a spectator. I can kind of ignore him. So they've got the zinc and the nitrate swimming around in the beaker. The nitrate is a spectator, so we don't really care. And then you'll add a solid piece of zinc metal. So this is the zinc anode. And it really is, I'll just take like a chunk of zinc, like a solid piece of zinc. Wonderful. There's your anode. Your cathode, your red cat. The reduction half was copper plus 2 ion in solution, aqueous, plus 2 electrons, forming solid, copper. That's a funky looking S. Solid copper. Okay, so again, we have similar components. We would have probably 1 molar solution of zinc nitrate or something like that. The nitrate is irrelevant, it's a spectator. And then we'd have a piece of solid copper, and it's really just going to be like a chunk of copper metal. All right, so those are the anode and the cathode. You've got the 2 half reactions separated into 2 containers, 2 beakers. All right, so let's see what happens as this thing starts to clip along, huh? Okay, so on the anode side, the oxidation side, the solid zinc is supposed to form zinc ions. Okay, so watch what happens. The zinc metal will enter the solution. I should use like a darker color. I shouldn't use blue on blue. I don't know, let's try black. Notice here that they're like kind of showing the mass of this zinc metal deteriorating on the bottom. That's awesome, because the solid zinc forms more zinc ion. This zinc ion concentration increases as we form more zinc plus 2 ions. So that's what's happening in the equation too.
The solid zinc is supposed to turn into these zinc ions in solution. So I'm going to form more zinc ions. I'm going to reduce the mass of the zinc anode. Make yourself a note. You can kind of tell this mass decreases. Now if I let this run for an extended period of time, you might kind of notice it on my zinc anode when we set this one up in class. But it kind of makes sense. It matches the balanced equation. Zinc ions are going to be produced, so that will increase in solution as I consume solid zinc. So the mass of that anode will decrease over time. What happens to those 2 electrons being produced? They go through this wire. So the solid zinc will be connected, it could be connected directly to the solid copper, but we'll run ours through a little voltmeter too, so that we can measure the voltage going through the system. So these poor little electrons then are going up through this wire. So if we wanted to be even more specific, there would be 2 moles of electrons going through the wire. All right, so now let's see what happens on the other half. This time I'm supposed to take those zinc, or I should say copper plus 2 ions, and form solid copper. Well, look at this. Can you kind of tell here that the mass is increasing? They're trying to show that there's more solid copper being deposited on the electrode. That's not supposed to be a negative sign or anything. Oh yeah, because I'm forming solid copper. That matches the equation. So you should see the mass of this copper electrode increase. Where is that copper coming from? It's coming from the copper ion in solution. This copper ion is turning into solid copper as it gains 2 electrons. So this guy, the concentration of copper ions will decrease. So these 2 electrons are going to flow through the wire. Then they're going to flow through my piece of copper metal. And this kind of makes sense. Momentarily this piece of copper metal becomes negatively charged. Those copper plus 2 ions in solution are attracted to that negatively charged piece of copper metal now. They'll pick up 2 electrons per mole and deposit as solid copper. Okay, so I should understand, are the ion concentrations increasing? Are they decreasing? Is the mass of the metal anode or cathode increasing or decreasing? It just matches the balanced equation. When we run this thing in class, our voltmeter should hopefully read about 1.1 volts. That's kind of what they're showing on this voltmeter. And we'll be able to calculate that later on in the chapter, what is the current flowing through the system. This should conduct about 1.1 volts. Here's the other thing we should mention. What's this funky thing in the center? This so-called salt bridge and cotton plugs. Well, that sounds exciting. Okay, so here's maybe another snapshot of that same setup, the same galvanic cell. So in a nutshell, here's what I'd want to be able to label. I'd want to label the oxidation half, the reduction half. Piece of cake. We had that on the last one. I'd want to know, is this ion concentration increasing or decreasing? We said that this ion concentration will increase as this mass decreases. Mass decreases. According to the balanced equation, which was the zinc solid forming the zinc plus 2 ion, and then those two poor little electrons will flow through the wire. There were two. Through my voltmeter, then those two little electrons are picked up on the other half by the copper metal, the copper cathode. On the copper side, we said this mass will increases, and this ion concentration will decrease. And that matches the balanced equation. We're going to pick up those two electrons flowing through the wire. They'll be attracted to the copper plus 2 ions in solution, and then we'll form solid copper. Fabulous. And this is the anode where oxidation occurs, and a red cath. The cathode is where reduction occurs. Okay, so now here's the problem. Here's this whole salt bridge thing. In order to keep this system running, the solutions need to remain neutrally charged, which is, I guess, kind of an oxymoron. The solutions need to remain neutral, and there is no charge. The solutions need to remain neutral. That's not going to happen. As we form more zinc ions, here zinc is flowing from the solid into the solution. As I increase the concentration of zinc plus 2 ions, the solution becomes more positive. In order for these things to sustain themselves, the solutions need to remain neutral. I mean, it starts neutral. They don't show it, but there would have been like 2 ions of nitrate for every 1 ion of zinc. But as I increase the concentration of zinc, and I'm not changing the amount of nitrate, the solution is going to become more positive. The opposite's going to happen on the copper side. As you decrease the concentration of copper ions because they're depositing as a solid, the solution becomes more negative. Because again, there would have been 2 moles of nitrate per every 1 mole of copper. I'm losing copper ions, so I'm left with a bunch of nitrate. The solution is going to become overall negatively charged. I don't want that. I want the solutions to remain neutral. That's the purpose of a salt bridge. So I'm going to use like a piece of dialysis tubing. Or here it could be some kind of a tube that has these cotton plugs, or some kind of like a porous membrane where particles can move through the membrane. The salt bridge is usually filled with some kind of ions that are usually spectators. So sodium and nitrate are very common. A sodium nitrate solution where sodium is not going to react with anything. It's not going to react with the zinc ions or the copper ions, and neither will nitrate. Both of them are totally spectators. So you're going to see a lot of like nitrate, maybe some chlorine if that's a spectator, as long as it can't react with anything in the solution. You might see like sodium or potassium. It's going to be a bunch of spectator ions. So you fill this salt bridge, which again, it could be any kind of a porous membrane, with some kind of a solution of spectator ions. As you increase the concentration of nitrate and this solution becomes more positive, the negative nitrate from the salt bridge will diffuse into the solution. So if you keep increasing the amount of nitrate, that'll help keep the solution neutral. That'll match up with all the extra zinc ions that are being formed. On the opposite side, as the solution becomes more negative because I'm losing copper ions, the sodium ion in the salt bridge will diffuse into the solution. It's totally a spectator, so it's not going to react with anything, but it helps to keep the solution neutral. That's the purpose of a salt bridge. Keep the solutions neutral so that we can keep the electrons flowing through the system.